Okay, well, I do want to get started because this is a pretty fully loaded lecture, and it is in fact a backloaded lecture. So I want to try to get through the front matter as quickly as I can, so that we can get to the stuff that's particularly useful for the project that everybody's working on right now. So you can see that this is about multi-threading. We already started talking about that last time. And we started to dabble in the question of how to synchronize things to make sure that we have correct code. And we're going to talk about that a lot more today. Race conditions are the issue where two logical control flows can, how shall I say, they interact with shared state in such a manner that depending on the order that the control flows reach this shared state manipulation, the outcome can vary in ways that are incorrect because, well, I won't go into that too much, but that's basically what a race condition is, where an absence of synchronization yields spurious results of some form or another. And so we have to be careful about guarding these circumstances where shared state is managed. And the way that we identify those sections of code, we call them critical sections. And we are basically saying this portion of code has to be executed atomically. Like, we can't have any other control flow that interacts with this state at the same time as the code in this critical section, or else we'll end up with spurious results. So that's kind of the idea behind a critical section. And mutual exclusion is just the mechanism by which we protect critical sections. We guard entry into the critical section. We basically have something at the beginning of the critical section, typically involving some kind of mutex lock. There's many different kinds of locks. I'll give you a brief tour today. And the idea is, if you don't have the lock, you don't get to enter the critical section. You have to wait until, whoever is in there has completed and released the lock at the end, and then you can acquire the lock and you can enter the critical section. So the idea is we only have one control flow through the critical section at any given time. There's a lot of different tools to do this, and Pintos specifically includes many different tools. Semaphores are probably they're the oldest one, and they're so unbelievably useful. And then read-write locks are also a very powerful tool. I don't think Pintos provides a read-write lock, if I remember correctly, because you have to write one as part of the 5th project. But it's got many other types of synchronization primitives that you can use for making sure that your operating system behaves correctly in this concurrent execution kind of scenario. Okay, yeah, and they block. So you can notice here it says in the slide that these locks block threads, and we expect that to be passive waiting. So what we mean when we block a thread is that it stops being scheduled and it's now in some queue. And you'll notice that the Pintos semaphores have queues built in, and when a thread becomes unblocked, it's removed from the queue and added back to the ready queue so that it can start executing again. So there are other tools that are often necessary, and we're going to talk about some of those today. I will also mention, probably several times in this discussion, that semaphores, mutexes, read-write locks, and all these other kinds of synchronization primitives often also include the ability to try to lock them. So instead of just saying, I want to lock this mutex, and that operation may block, you can instead try to lock it, and if the lock is not available, then you don't block, you just go on without having successfully acquired the lock. Now you might say, well, I can't execute the critical section if I haven't acquired the lock, and you're right. Basically, the way that code is written when you have try operations is you try to lock something, and if you fail, you just don't do the thing you hope to do. So that's a way that you can use locks without blocking, except that you may not get to do the thing that you hope to do. So that's the way that mechanism works. We're generally not going to talk about it because most of the time when we're doing things, we want to successfully lock stuff. So we block and we wait until the lock is available. Okay, there are software solutions for mutual exclusion, which is very interesting. I wanted to point out Peterson's algorithm simply as a representative example is the term I'm looking for here. And so this is just sort of a little, how shall I say, example of how one can create a purely software-based mutual exclusion mechanism. And it's kind of interesting. You've got these flags for processes PI and PJ, or in this case, 0 and 1. And the flag basically states a desire or an intent to enter the critical section, but you always say it's the other person's turn. And so then you sit in this while loop, which basically you sit and wait until the other thread says, I'm not in the critical section and I'm not interested, you go ahead. And so it's a very interesting kind of selfless mechanism, if you will, where processes or threads can cooperate to make sure that they enter a critical section when the other process is not in it. Now, this is, again, this is just to show you, this is sort of a historical interest. It's not something that's particularly relevant, so I'm not going to spend very much time talking about it. There are a number of ways that have been devised, and they basically all have the same characteristic. The example, again, that I showed you was contrived for a number of reasons. One is that it only involved two processes or two concurrent threads, and another is that it was busy waiting. And so it's clear that a software solution would require finessing if you wanted to improve its characteristics. And it turns out that there's much faster ways of doing this with hardware support, which is why all the solutions we use are hardware-based by now. So I already mentioned problem one. The other thing that I wanted to mention is actually really crucial, which is that out-of-order execution is a huge problem when you're writing an operating system. What do I mean by out-of-order execution? Well, two things are in the mix that will reorder the steps that you issue in your code based on what might actually be faster, but still be equivalent to the code that you wrote. And the compiler is willing to do this all the time. The compiler will reorder the instructions in your code to achieve faster execution if it possibly can. And processors themselves, especially the x86 processor family by now, will reorder instructions in unbelievable ways to achieve greater throughput of instruction execution. When you have out-of-order execution, it frequently destroys the synchronization mechanisms that we built. And so we have to figure out ways of working around this. And I'll show you a few details of this, and it'll become even more important next time when I show you a special thing that Linux does. So modern systems do have hardware solutions for this. Normally what they involve is atomic operations that you can use to lock a mutex. And they're very efficient. Like you can build a mutex with 1 byte on x86 now, although typically you use 1 word. So you would do like 4 bytes or 8 bytes for a mutex, which is still incredibly cheap. And there's individual instructions you can use for doing this in one instruction that work on multi-core systems. So it's very inexpensive on most processors to build mutual exclusion mechanisms. So so like I say here on the slide, if we wanted to use a software-only solution, which we don't because they're slow, we would still have to leverage the hardware to work through these out-of-order execution issues that we would run into very rapidly. Typically, we talk about barriers when it comes to implementing locks in operating system implementations or standard library implementations. A barrier is basically a thing you can plop into your code to make sure that everything before the barrier has finished before anything after the barrier starts running. So basically, it's a point in time where you're saying everything before this point has to have finished, and then you can go on to do the next thing. So don't reorder across this barrier. That's the idea behind a barrier. So there's two kinds of barriers we care about because, as I mentioned, compilers can reorder instructions and processors can reorder instructions. And we have to have a tool to deal with each of these. So an optimization barrier is for telling the compiler, don't reorder across this boundary. And so as I say on the slide, this affects the compiler's output, but crucially, it doesn't prevent the processor from reordering across that boundary. So that's quite an interesting little detail here. Here is the, well, I should say a very typical barrier macro in C, or you could use it in C++ as well. It uses the assembly language directive with the compiler. But you'll notice the way that it's written. It's a pound-defined barrier, so this is the name of the macro function that we're defining. ASM says we have some inline assembly, but we don't have any assembly. It's a no-op. But what we do is we tell the compiler everything changes after running this assembly snippet. So what we're basically doing is telling the compiler, you can't really trust anything when you see this barrier thing, and that prevents it from making any optimizations across that boundary. Okay, so it's funny to me that this exists, but it's incredibly useful for preventing the compiler from making optimizations that reorder instructions across this barrier in the code. And you can find Pintos has this in its implementation because even though it only runs on single core, there are points where you need to make sure that optimizations don't interfere with the ordering of operations. Okay, so yeah, you can use this to ensure that one operation is completed before the next operation is started. Okay, and yeah, so lock acquisition tends to be an example of where we use an optimization barrier, because if you have the code that says acquire a lock, and then the code that starts the critical section that needs to be protected by the lock, you better not have the compiler reordering those things into a different ordering, and then your lock isn't actually protecting what you need it to protect. So you put it's very often that you see an optimization barrier within a lock acquisition implementation or a lock release implementation. Okay, optimization barriers are necessary but not sufficient because the processor also has the ability to reorder operations. And so the other kind of barrier is called a memory barrier, where we basically prevent the processor from reordering instructions in certain contexts. Okay, so as it says on the slide, all the instructions before the memory barrier are completed and resolved, we say, before any instructions after the barrier begin to execute. Okay, and so as I say here, oftentimes OS implementations will have a macro, another C macro that inserts a memory barrier, and the memory barrier also will include an optimization barrier, because if we don't want the CPU reordering, almost certainly we also don't want the compiler reordering across that boundary. So the memory barrier macro will typically also include an optimization barrier. Okay, we have different kinds of barriers depending on what we need to do. If we need to make sure that reads occur in a certain order, we can use a read barrier that allows writes to still be reordered across the read barrier. Correspondingly, a write memory barrier says writes have to occur in a certain order, but reads are allowed to be reordered across the barrier. And then you can also have just full-on barriers that specify a constraint on both reads and writes. So let me see. There's this is a really interesting thing. You'll notice in Linux, especially if you're reading the Linux system internals book, that it talks about SMP, MB, RMB, and WMB. The SMP stands for symmetric multiprocessing. And the idea is these macros will insert a barrier if you are running on a multi-core system, but they will turn into no-ops if you're on a single-core system. Because remember, you get different kinds of parallelism or concurrency if you're on a single-core system versus a multi-core system. And so, if you're on a single-core system, you may not actually need a barrier because of the way that the processor operates and how the operating system operates. So that's kind of an interesting little nuance. Okay. Let's see. Process. Yeah. So, there are typically hardware instructions for this. That's how you tell the processor don't reorder. And so IA32 has these instructions. X86-64, of course, also has these instructions. So LFence is a load fence, SFence is a store fence, and MFence is for both loads and stores. Now, there's other situations where you almost always want to make sure that the stuff that happens before the operation completes before the stuff after the operation starts. And so other instructions in x86 are also defined implicitly as memory barriers. One example is IRET, and that should make total sense. I want the interrupt handler to finish what it's doing, and then IRET operates implicitly as a fence for the things that happen afterward, because we want to see all the instructions that are part of the interrupt handler resolved before we see anything after the handler returns start to execute. Okay, there's a few other things as well. And IA32 is actually a super helpful instruction set architecture. It already imposes certain constraints on read ordering and write ordering that are very friendly to writing lock-free code and low-level operating system code. Other processor architectures can be really nasty. And so that's one of those things where if you only ever spend your time on x86, you might get a little spoiled because other processor architectures are a lot less multi-thread friendly or concurrency friendly when it comes to the way the processor behaves and the kinds of extra steps you have to go through to make things correct. So kind of an interesting thing. A simple solution, and I mentioned this last time, to making sure that a critical section is properly enforced is disabling hardware interrupts. And this is one of the techniques that you will use definitely in this project, the first Pintos project, because you may have code that's executing in a trap handler or code that is not part of an interrupt handler. And you want to make sure that if an interrupt handler goes off that could muck with that state, that situation doesn't occur. The easy way to do it is just turn off interrupts while the shared state is being manipulated. That way you can guarantee that no interrupts will fire. Okay, so IA32 has CLI clear interrupt flag and STI set interrupt flag instructions for doing this. And that way you can turn on or turn off interrupts. If I remember correctly, Pintos has some helper operations that do this for you, like inter-disable, inter-enable, or something like that, so that you can easily turn them on and off from C. And if you go look at those implementations, they have a little bit of assembly code that just uses the CLI and STI instructions to turn off and turn on interrupts. Okay. One important key is that if you're on a multi-core system, these instructions only turn on and off local interrupts. So other processors may still be having interrupts fire, and if they do, and they're manipulating shared state, you now have problems. And so you have to take extra steps if you end up on a multi-core system, if you're writing a multi-core operating system, so that other processors won't trample on shared state that you might be trying to manipulate. So a technique that is frequently used is called a Spinlock. As I say on the slide, it is possible to disable all interrupts across all processors, but this is sort of a tool of last resort. You only use it when no other option will work, because it basically causes there to be a significant increase in latency from interrupts occurring to them being serviced. And that can have some pretty negative effects on the scheduling characteristics of the operating system. And so there's another technique that people use called a Spinlock, which you may have heard of. It's probably, I think the name is very apropos given how it works. Basically, when you try to acquire a Spinlock, if it's available immediately, you acquire it. It's yours. If it's not immediately available, you busy wait. You actually spin in a loop, checking periodically if the lock is now available. So that's why it's called a spin lock, because people who try to acquire it will spin on it until it becomes available. Now, spin locks should only ever be used if you have multi-core system or multiple processors that are executing. Like, you have to have true parallelism for a spin lock to make any sense. The reason why is I think pretty clear. There's two contexts in which you could try to acquire a spin lock. One is obviously interrupt context, and the other is process context. Now, if you're on a single core system and you're in process context and you spin on a spin lock, there's only one core. You're the only one executing and you're spinning. So what happens is you use up your time slice and you're kicked off the processor. So you just wasted a bunch of time. It would have been better to just yield. If you're in interrupt context, you're still the only thing that can run on the processor, but you have to run to completion. So you can't give up the CPU. So you spin and you spin and you spin and you spin, and nothing else can possibly unlock the spin lock. So you've locked up the system basically. So spin locks only make sense when you can have multiple cores and one core is waiting, spinning, and the other core, code on the other core, can release the spin lock and allow this core to go on. So that's one of those key details. If you ever end up in a situation where you're working on some system and somebody says, I want to use a spin lock, but it's a single core system, tell them no, they're doing it wrong. So you have to have a multi-core system to use spin locks effectively. Okay, so two scenarios prompt spin lock use. One is you can't context switch away from the control path. So you're in interrupt context. Spin locks are basically the only kind of lock you can use in interrupt context. The other possible scenario is that you expect the lock to be held for a very short period of time and you don't want to context switch away. Spin locks ideally are granted in under like 20 to 100 instructions, 20 to 100 clocks. If you're going to hold it longer than that, then you start thinking about simply context switching away, okay? You could probably even spin for longer and still see a benefit. But remember that context switches are expensive, and so if we expect the lock will be held for a very short time, spin on it, because then you are avoiding the overhead of a context switch. But you still need to be multi-core. Okay, there's a lot of stuff that's talked about here. I think that what I'll do is spend a little bit of time talking about this, but I don't want it to spend too much time because spin locks are not actually relevant to Pintos, and there's other stuff that is relevant to Pintos that I want to talk about in this discussion. So interrupt handlers can use spin locks on multiprocessor systems to guard shared state from concurrent access. You basically spin on the lock in the interrupt handler, expecting someone on another processor will release the spin lock. Once you've acquired it, you manipulate shared state, and then you release the spin lock, and you're done. So you haven't ever passively waited the entire time of the interrupt handler. So a simple example would be if you have a timer interrupt. Let's say you have a 4-core system, and all 4 cores happen to have a timer handler that goes off at the same time, and they all manipulate shared state, and the timer interrupt handler uses a spin lock to guard the shared state. Well, somebody's going to get into the critical section first. They're going to manipulate the shared state, and since interrupt handlers are supposed to be short, they're going to come out of the handler fast. Then one of the other cores will acquire the spin lock, and they'll be able to do what they need to do, and then they'll finish fast, and so forth. So you can see that the spin lock is held for a short period of time, and that's the real key for when it's appropriate to use a spin lock, okay? So that's basically it. I don't know if anybody has any questions about spin locks. If you do, feel free to throw them into the chat or to speak up. But I'm actually going to move on because, like I said, this isn't super relevant to the Pintos discussion. I will at least show you the slides because I want you to see the slides. There's some information here that you can look at, how you can get into trouble with spin locks, and then here's a bunch of guidelines for spin locks as well. So if you're really intrigued by the idea, feel free to read these slides and you can ask me questions or whatever about them later on. But Spinlocks are basically the one kind of lock you can use in interrupt context if you're on multi-core, and they're very effective. They're used heavily by modern operating systems, which obviously support multiple cores. Okay, one issue that can occur with locks is the specter of deadlocking. You've probably heard of this concept. I don't know if any of you have experienced code that has deadlocked, but you probably will in this class in particular. Basically, you can have a set of processes that become deadlocked, which means that none of them can make any progress because each of them is waiting for someone else to do something. So as I say on the slide, a set of processes is deadlocked if each process in the set is waiting for an event that only another process in the set can cause. Now, you could also state this in terms of locks. Each process in the set of deadlocked processes is waiting for a lock that some other process holds, and every process is holding a lock that another process is waiting for. If you have a situation like that, you have a deadlock. You can have 2 processes deadlocked. You can have 50 processes deadlocked. It's easy to construct such scenarios. So an important implementation detail is that deadlock actually has a recipe. There are 4 things you need to have deadlock. And if you don't have those 4 things all present, then deadlock simply cannot occur. And so a lot of systems will try to engineer out the potential for deadlock by making sure that one of these 4 things is not present. So let's go through these real quick. One is that you have mutual exclusion, so resources that can be held in a non-shareable mode. Well, that one's hard to get rid of because we need mutual exclusion in order to implement critical sections. Hold and wait. A process must be holding one resource and waiting to acquire another resource that is currently unavailable. Okay, that's another one that can be challenging. No preemption. A resource cannot be preempted. The process must voluntarily release the resource. What we mean by this is if a process is holding locks on resources and that's hindering another process who wants one of those resources, the first process can't be forced to relinquish its locks. That's what we mean by no preemption. And then you have circular wait, which is that you could order the processes so that the first one is waiting for the second one is waiting for the third one is waiting for the fourth one, all the way up to the last one. The last one is waiting on the first one. So you have a cycle in the dependencies on resources and locks across all of the deadlock processes. Okay, if you have these 4 things, it's a matter of time before your system will deadlock. So there's about 3 different ways that systems deal with this issue of deadlocking, and it's very interesting to me that we have these 3 different ways of doing it. One is deadlock prevention. This is what we do in operating systems. We design the OS so that it will never deadlock, because if it deadlocks, we view it as a bug, which is true because it's the OS implementer that created the potential for deadlock, and so they shouldn't have done that. So we fix the bug. Usually we try to break either the no preemption or the circular wait requirement of deadlocking. So no preemption means that if you run into a situation where it looks like you have a deadlock, you have to give up all the other resources that you hold. So that basically means if somebody else is waiting for something that you're holding and you can't get what you need, you give everything up, and that allows other people behind you to proceed. So that breaks the deadlock potential. Circular wait is extremely common. Basically what we do is we have a total ordering over all the lockable resources, and all the processes are required to follow the same total ordering. And basically, if you have a total ordering like this, it's not possible to generate a cycle in your deadlock. As I say on the slide, let's say you have a total ordering of resources and you acquire resource 2, and then resource 6, and then resource 19. So you have a total ordering across the resources that you're locking. And then after locking 2, 6, and 19, you go back and say, I actually want to lock resource 4 now. Well, you're doing it out of order. So you have to give up all your locks, and then you start again at the beginning. 2, and now 4, and then whatever the other ones were that I named. So you always have this total ordering, and if everybody always follows the total ordering, then you can't generate cycles. And this is a pretty important result. This is the technique that most systems follow when they're trying to prevent deadlock. Okay, there's another approach that people use, which is deadlock avoidance, which basically is that the system has to be very clever, and it simply fails lock requests or resource requests when it senses there is the potential for deadlock. So it basically tells processes, sorry, you can't do what you want because a deadlock would occur if you did. So as it says here, the system detects when allowing a request to block would cause a deadlock and instead immediately fails the request. There's a number of algorithms you can use to do this. I'm just going to throw these up here. They're not very relevant for OS implementation, and certainly OSs can provide this kind of mechanism to applications, but that's about the only context that I've ever seen deadlock avoidance used. Then you have one of my other favorite approaches, which is deadlock detection and resolution. So what systems do in this context is they allow the deadlock to occur, and then they simply find out, hey, there's a deadlock, and then they take a step of some kind to resolve the deadlock. Typically, like I said, you have a set of processes that have a cycle in their dependencies, their lock requests. And so the deadlock detection and resolution is find the cycle and kill one of the processes, because that breaks the cycle. Now everybody else is allowed to continue. And it's pretty wild, but this is what databases do. Databases have the potential to deadlock, not the implementation itself, but requests for data that come in from various clients interacting with the database can acquire locks on the data in any order. This is why databases have to do this. And so the database implementation just pays attention to when a deadlock occurs, and when a deadlock occurs, it picks up a client and terminates that transaction. Very, very common. It may sound crazy that this is the way that it works, but it's actually not that big a deal. So typically, as OS implementers, we go for the deadlock prevention mechanism. We go for deadlock prevention because we want to write nice operating systems without bugs. Okay, if you have any questions about that, feel free to ask. Otherwise, we will start talking about more primitives. Semaphores are probably my favorite thread synchronization mechanism because they're just so generally useful as a tool. They were devised by this guy you may have heard of named Edgar Dijkstra, and semaphores basically allow processes or threads to coordinate actions between each other. When you have a process that's trying to acquire the semaphore, if it's not available, the process blocks and it just waits. And so what this means is that you can't use semaphores to guard shared state. Now I have to be careful what I say here, because one of the solutions for Pinto's project 2 for the thread sleep mechanism is to use semaphores. Well, use them in a non-blocking way. What's a non-blocking way? Well, you can signal on them. Signaling on a semaphore doesn't block the interrupt handler. But if you try to wait on a semaphore and it's not available and you block, you definitely cannot do that from interrupt context. So semaphores have a simple state value. It's an integer, and it's defined in a number of ways, but we're going to keep a really simple definition where we say the value of the semaphore can't be negative. So it can be 0 or it can be non-zero, but it cannot ever go negative. And then you also have a queue of waiting processes or waiting threads on the semaphore. You have these two operations, wait and signal, which are oftentimes also called down and up. Dijkstra actually had, oh, I want to remember, is it Dutch? But it's a foreign language that I don't, none of us probably speak. And so you had probeer te verlagen for try to decrease, and then verhogen, which is increase. And so, but I like wait and signal a lot better because they're a little bit clearer. But wait decrements, if it can, because remember, we keep that value at 0 or higher. It can't go negative. And signal increments the value. So this would be an example wait implementation. While the semaphore value is 0, the thread puts itself onto the waiting list, and then it passively blocks. And so what that means is it stops being scheduled. Now, once you get to the point where you're awake and the semaphore value is positive, then you're able to decrement it without it going negative. So you go ahead and decrement the semaphore value. Signal works in the inverse manner. Basically, it increments the value, and then since it's incremented now, a blocked thread can proceed. And so the signal mechanism also checks the waiting list. If there's anybody in the waiting list, then it picks a thread from the waiting list and unblocks it, because now it can proceed. Now that looks really simple, except that these are critical sections, because they're manipulating the shared value that is used for signaling. And so all of these operations have to be done in a critical section. Okay. And if you look at Pintos implementation of wait and signal, you'll see that these things are guarded by turning off interrupts. It's not possible for an interrupt to go off within that section. And since Pintos is single core, that's all it's got to worry about. If it were multi-core, then you'd have to probably have a Spinlock to guard it as well. Okay, so block threads, yeah, so they're managed in various ways. Typically, semaphores are implemented in the most efficient way, which may not necessarily be fair. What do we mean by fair in this context? Is it necessarily a given that threads acquire the semaphore in the same order that they request it? The answer is almost never. Can you provide these kinds of guarantees? You might be wondering, and if you aren't, you should be wondering, why do we wait in a while loop? It's really crucial that you wait in a while loop. If you change that while to an if, the semaphore breaks. And I'm not going to explain why in the class because I don't have time, but it's really important. And so this is one of those things that you have to do it this way, and it all has to be guarded with a critical section. And threads can still acquire the semaphore in a different order than they requested. And that's just life. You try to write your code to not matter if it behaves that way. Okay, counting semaphores. So a semaphore's value represents how many times wait can be called without blocking. So this is the meaning of the value in the semaphore. And so as it says here, when you have it be some value other than 1, like 50 or 6 or whatever, you're basically representing how many instances of a given resource are available. And so you call them counting semaphores when they're used in this way. And this is interesting because it doesn't ensure mutual exclusion, but it does ensure that the semaphore is only granted up to a certain number of times. And a bounded queue is a really great example of this. Let's say that we want the queue to be friendly to multiple threads requesting and publishing values. Well, what if we have 5 values in the queue? We want to make sure that requesters can request 5 values and then they passively wait. So we can use a counting semaphore to represent how much data is in the queue. So when a writer puts a value in, it signals on the semaphore saying there's another value. So the value, remember, the semaphore's value gets bumped. And if a reader wants a value, it can wait on the semaphore. And when it acquires the semaphore, it knows it has a value to read because the value will be decremented. Okay, and then that's that reader's value. So this is a very clever technique. You can use another semaphore for writers to make sure that there's space in the queue if you want to keep it bounded. You can say the semaphore's internal value is how many spaces there are available to write to in the queue. And then writers can wait and readers can signal on the space semaphore because the reader is removing a value and creating some space so a writer could then proceed. So counting semaphores are a really powerful mechanism. Now, so let's say that we were building a bounded buffer and it had these two semaphores and we have these operations that are occurring. It turns out that you need a third semaphore to make sure that readers and writers don't trample on each other's toes when they're manipulating the internal queue state. And so you have a third semaphore, which you use to enforce mutual exclusion. So its value is only ever 0 or 1. Okay. And so in this kind of context, the semaphore would be called a binary semaphore because the binary semaphore is being used for mutual exclusion as opposed to counting how many instances of a resource are available. Okay, so you can see that, I mean, there's no difference between a binary semaphore and a counting semaphore. You're just sort of indicating the semantics of how it's being used in that context. So probably in the vast majority of places in your Pintos implementation, you will use semaphores as a mutual exclusion mechanism or as a signaling mechanism, okay, which is actually the next thing to talk about. Because there are also these things called mutexes. Mutexes are basically an optimized binary semaphore. You know, since it's used so frequently, why not just build a special thing that's super fast and efficient? So we don't do addition and subtraction. We can actually use these bit, set, and test operations that the processor provides to build mutexes that are very efficient. Okay, so as it says here, the main difference between mutexes and binary semaphores is the notion of ownership. And this is, it tends to be the way that you see them used. A mutex is acquired and released by the same thread, 99% of the time. Mutexes are almost never used for signaling, but a binary semaphore frequently is used for signaling between two threads of execution. And I'm telling you this right now because binary semaphores are incredibly useful in Project 2. They're incredibly useful in Project 3 when you want one thread to wait until another thread is doing something. You'll see this pattern rather frequently in Pintos. So the one thread goes down on a semaphore because it's waiting for some other thread to do this thing. When the thread is done doing it, it signals, so it goes up on the semaphore, and that tells the first thread that it can now proceed. You'll see that frequently within Pintos. Okay, yeah, as with semaphores, mutexes are formulated to block processes, but you can also use a try lock on a mutex as well if you're in a situation where it's okay if you can't do the thing that you hope to do. All right, yeah, and I already mentioned this. Exchange or bit test and set operations are used to build mutexes. Very straightforward mechanism. Okay, let's see. Yeah, there's a lot more to talk about with all of this stuff. Condition variables are in Pintos as well. I don't think you need to use them anytime soon, but I can't remember. But there's a lot of other kinds of mechanisms that exist around this stuff. I'm just going to throw this all up here because the point of the slide is this is only the very beginning of the topic of concurrency and parallelism. And I wish that I could teach a class on this because then you could get into lock-free and all kinds of other stuff. We'll talk a little bit about this next time. It's a fascinating topic. But hopefully this will be sufficient to start you underway in some of the Pintos implementation stuff. And we will cover more details on this topic as they become necessary through the course. Okay, next thing to talk about, this is the last thing that I want to talk about today, so hopefully I can get through it in 7 to 10 minutes. Kernel programming is really different probably from anything that you've ever experienced before, unless you've done embedded systems programming. So I wanted to take a little bit of time and talk about this and introduce you to some of the things you're going to see as you get into the Pintos code. You probably already started to notice some of these things. First of all, we care a lot about efficiency, and this includes efficiency of memory use and also efficiency of computation. System code often has fewer resources to use because it's trying to be as small as possible to leave as many resources available for applications to use. The other thing is that if the kernel is fast, it benefits everybody. If the kernel is slow, everybody will suffer. And so trying to make sure the kernel is small and fast and efficient pays off across the board. And so that's a big reason why we try to be efficient in how the kernel is implemented. Common problem. You'll be seeing this problem all the way through Pintos. You need to manage a linked list of items. Now, if you were writing a linked list in Java or Python, or you were writing a linked list in C++, you would probably create a node type that represented the linked list. You'd have something that's the head of the list, and you'd have these nodes that know what the next node is. And maybe if it's a doubly linked list, it would point back to the previous node as well. And then the nodes would point to the payload somehow. They would oftentimes point to the thing that's actually the element. Maybe if you're doing this in C++ and you're working with templates, you incorporate it into the node, but a lot of times, especially in Java, the element itself is going to be referenced across a separate memory allocation. Now, the kernel doesn't have a general purpose allocator. We're going to talk about kernel allocators in a few lectures, and you'll see that they tend to be very specialized in how they operate. So we kind of can't afford to incur the overhead of a general purpose allocator or the overhead of the header and the footer and all that kind of stuff that goes along with every allocation. And so the kernel will use a technique like this. It's called intrusive linked lists. I don't have that on the slide anywhere. So if you want to look this up yourself, you can look up intrusive linked lists. But you can see that you have the data structure that needs to be in a list, and the linked list is just built in. And that's how the mechanism works. The pointers themselves don't actually point to the next element. They point to the next pointer. And so this picture is drawn literally how it's done. The list one points to the next one member of the struct, and that next one pointer points to the next one pointer of the next struct, and so forth. You're actually threading the pointers together. Okay? And so if you have the pointer, you have the address of next one, you can figure out the address of the start of the data structure, but you have to do an extra operation. And so this is an example of it where you're taking the pointer, which would be next one, it would be the address of next one. Then you go ahead and figure out where is that in the struct, and you shift the pointer so that you're pointing to the start of the struct instead of pointing directly to the pointer. Now you might look at this and say, why the hell would I ever want to do this? You're right, it sucks. Fortunately, you can wrap it in macros. And when you're looking at the Pintos macros, that's what it's doing for you. It's doing literally this trick. And you might say, that's dumb and I hate it, but this is how most operating systems actually implement linked lists. They use an intrusive linked list implementation. One of the reasons why you can do this is so that you can actually have multiple linked lists that link all these things together, okay? So you can see here that now we have two lists of our elements, and they're linked together in different orderings. And so having each pointer point to the actual location of the next list pointer allows us to do this relatively easily. I'm not saying it's nice. You wrap it with your macros and abstractions so that you can make it as nice as possible, but it still kind of sucks. I'm going to be completely honest with you. Okay? So you can wrap that in macros to simplify type declarations. So that's one trick you see frequently. It's called intrusive linked lists. Another thing that you'll see is avoiding dynamic memory allocations whenever it's possible. So you see that we had this example, and this actually corresponds to the way that thread queues are implemented in Pintos. Remember that the thread is a page. It's an allocated page because it's the unit of virtual memory allocation. So the page allocator is very simple. It's just got like a bit vector saying whether each page is used or not. So it can say page allocation, very simple. Find the next 0 bit, change it to 1, and now the page corresponding to that bit is yours. So the page allocator is very fast. And so as it says here, the list elements are thread structs, and we don't have any dynamic memory allocation at all. We don't have a separate node type that links all these things together. We link the thread structs together directly. And so it's a very efficient way of doing this with a minimum amount of memory management. Here's another example. Let's say that you need a linked list of nodes, but you know that the linked list has a maximum size, and you know that most of the time, the linked list will either be completely full or mostly full. Do you want to dynamically allocate nodes in this scenario? The OS answer is definitely not. What happens instead of dynamically allocating each node individually is that the OS implementation will have a static chunk of memory, so statically allocated. This part of my memory is for the linked list. You allocate space for all the possible nodes you need, and then you just have the next pointers linking them in whatever order they need to be. So what have you done? You've saved needing dynamic memory management. You've saved the overhead of a header and footer to manage dynamic allocations. You've basically done this as efficiently as it possibly can be. And all you really need to do to reorder the list or pull stuff off the list or put stuff on the list is just manipulate the next pointers. Memory allocation becomes a non-issue. Okay? Very valuable. Now, as far as interrupt handlers, I think this is the last thing to talk about. We're going to go over time a little bit. Handlers need to run as quickly as possible. And so you oftentimes are faced with a choice between doing work in interrupt context or doing it in process context. And if you think about that, if you do it in process context, that one process is slower. If you do it in interrupt context, everybody is slower. So almost always when you have a choice, you do work in process context to save work in interrupt context. Okay? The thread sleep functionality is a perfect example of this kind of approach. You have state that you need for figuring out when threads should wake up. You could either store the clock tick of when it went to sleep and how long it's supposed to sleep into the thread, and then the interrupt handler would have to do some math for each thread to see if it should wake up. Okay, take the time that it went to sleep plus the time that it needs to sleep and see if it's past the current clock time. That's work in the interrupt handler. Instead, the thread sleep operation could just calculate when the thread should wake up. Now the interrupt handler just needs to look at the value, and that's it. So you would much prefer to just do the work in process context and let the interrupt handler do as little as possible. Okay? So the second one is what we recommend for project 2. It'll make your code very fast. Oops, looks like I got my slide ordering messed up. Another thing that you could do is when you're storing sleeping threads, you're going to store them all in a single list. So you could order them in no particular order, which is fast for adding threads to the list. Or you could make sure that they're always kept in increasing order of wake-up time. And if you store them in increasing order of wake-up time, then the interrupt handler can just pull them off in order. And when it sees a thread that it can't wake up, it knows that all the threads after that also cannot be woken up. So that shortens the amount of the list that has to be traversed by the interrupt handler. So something like this is going to be a lot more efficient. Okay. And again, you want to use the second approach. Okay, I'm not going to talk about any more because I am really going beyond what we need to do, but you can read about all these things and ask, consider how they would be approached in your situation. But basically, the bottom line is that kernel programming and OS programming has a strong focus on avoiding allocations and avoiding performance issues. And so hopefully this will help you make good decisions as you go through your implementations for the remainder of the course. So I'm going to stop now because it's 1:59 and I apologize for going over. I will see you next time. Hope you have a good weekend.